All right, so today's lecture is on osmosis and water potential, and this is essentially just quantifying osmosis. And one of the ways you can look at this is that, and the way I want you to think about this as we talk about it, is that we mentioned before, and I said this isn't completely accurate, but I talked about salt sucks, right? That when you add sodium or add any solute to water, it is going to draw water towards it across a membrane. Okay, so if you have one side of membrane that has more water, or there's less stuff in it, and one side of the membrane where there's less water, there's more stuff or solutes in it, water's going to go towards or be sucked in towards that one side. Remember, it's not an actual salt doesn't suck, but water goes from a high concentration where there's less solutes to a lower water concentration where there's more solutes. Okay. We can quantify that as a negative pressure, and that's essentially what water potential is. So, remember, as I said, salt sucks, water flows where water isn't, or water flows from a high water concentration to a low water concentration. A solute can be anything dissolved in water. On the AP exam, they tend to focus on either salt, sodium chloride, or they focus on a solute like sucrose or glucose dissolved in water, okay, like a sugar. And as I mentioned, you lower water concentration always by adding solutes to the water. So osmosis is simply the diffusion of water across a membrane. Water will again flow from a high water concentration to a low water concentration, just like everything else. And remember, water cannot cross the membrane easily. It cannot because it is a polar molecule. Polar molecules don't cross well because they can't get past the hydrophobic tails of the membrane, right? So there's special facilitated diffusion proteins called aquaporins, which do allow water to get across, and they form a hydrophilic zone for water molecules to get through. And remember, the R groups on the inside of that aquaporin are also going to be hydrophilic. Did I say hydrophobic before? Hydrophilic. It provides a hydrophilic place for water to go through. I can't remember. And the water will go through there easily if the R groups on the inside are also hydrophilic. That's in contrast with the tails, right, on the outside of the protein that are interacting with the tails. Those are going to be more hydrophobic R group proteins or amino acids. So this is kind of showing you about water concentration and why it happens. Why is it that when you add solutes, the water concentration lowers? You can see that in terms of free molecules, when you add solutes, the water molecules will stick to those solutes depending on their charge or their polarity, right? And there's fewer free molecules on the solute side compared to the more pure water environment that's on in this case, the left side. So water is going to flow from that high water concentration towards where there's more solutes. All right, so here's a question that actually relates to water potential, and it feels like it's not going to, especially as we move through the course more. This is trickier actually on the actual AP exam because you would have learned other things in which we normally talk about diabetes through the scope of like hormones and ligands and things like that, but this is going to relate to water potential or osmosis. If an individual with diabetes consumes sugar that is in a high in simple carbohydrates, blood sugar levels can rise above normal levels. Which of the following questions would provide the best direction for a researcher who wanted to study the impact of abnormally high blood sugar levels on cellular homeostasis in diabetics? All right, so A, are cells in diabetics larger in size than those in non-diabetics? B, do the cells in diabetics have more potassium ion channels in the cell membrane than do cells in non-diabetics? Does water move from cells in blood vessels more rapidly in diabetics than non-diabetics when blood sugar levels are higher than normal? Or D, do the cells of diabetics use simple sugars as an energy source? So, as I mentioned, this is actually a transport answer, right? And a water transport question. And think about what we talked about. The answer has to relate to water transport and has to go in the correct direction. Remember, when you have high concentrations of solutes, water will be drawn towards that, okay? And I'm going to give you a second to think about this and come up with an answer. Okay. So the only one where that matches, right, is C. Does water move from cells in the blood vessels more rapidly in diabetics than non-diabetics when blood sugar levels are high? So inside the blood, they're going to have high sugar levels, and as a result, water may move into the blood, right? And that can actually increase. One of the side effects could be high blood pressure. because of high blood sugar levels. There's more solutes in the blood, therefore you increase their blood pressure. So C is going to be the best answer here. Let's see. Do the cells in diabetics have more potassium ion channels? That doesn't help. Direct wanted to study the impact of high blood sugar levels, right? So it has to relate to blood sugar, right? So the cells would actually be a little smaller because water would leave the cells and go into the blood, so A can't be right. B has nothing to do with blood sugar. It's talking about potassium ion channels. And then do diabetics use simple sugars as an energy source? Like they all do, but it's not talking about that's not really talking about cellular homeostasis. So C is the best answer there. All right, so before we get into water potential, which way will water diffuse? We kind of done problems like this already in class a little bit. We talked about it. And remember, water flows from a high water concentration to a low water concentration. So obviously what makes the most sense is water is going to diffuse out of the cell, right? From the where there's more water inside the cell towards where there's less water outside the cell, or where there's more solutes, right? Now we're going to get back to that in a little bit, okay? So this exact same problem, we're going to apply it to water potential. So tonicity terminology. These are three terms we've already kind of mentioned or talked about in class briefly, but remember, you always need two solutions to tango for tonicity, right? You can't just have a hypertonic solution. It's in reference to another solution, which would be hypotonic to it. So if there's a hypertonic solution, there must always be a hypotonic solution and vice versa. If it's an isotonic situation, that means both solutions are the same concentration that have the same ability to draw water towards them. Okay, so isotonic solution, equal concentration of solutes on both sides. Hypertonic solution is a solution that has more solutes in it or more salt in it, right, compared to another solution. A hypotonic solution has more water compared to another solution, or it's a waterier solution. So again, which is hypertonic and which is hypotonic? The hypertonic solution is going to be the one where there's more solutes or less water, so the outside is going to be hypertonic, and the inside is going to be hypotonic, where there is more of that water. And the way you can kind of remember that is hypo. And hypotonic, that's when it, or hippo, they think, like water is going to flow towards a hypotonic solution, and that means, or excuse me, if a cell is in a hypotonic solution, which is the opposite of this. Let's say we reversed these scenarios, and there's 90% water and there's 10% solutes on the outside, not the inside. Water is going to flow out, right? Water is going to flow in. I'm having trouble. If the 80% was on the inside and the 90% was on the outside, water is going to flow from the outside in, and the cell is going to get bigger. So when the cell is in a hypotonic solution, it's going to get bigger. If it's hypertonic, so if in a hypertonic solution like this scenario, water is going to flow out, and you would expect the cell to shrink because water is going to flow where there's more, towards where there's more solutes and less water. So in this scenario, there's a hypotonic solution inside the cell and a hypertonic solution outside. Again, right, we talked about all of these scenarios already in class. And remember, in plants, though, they have that turgor pressure, which we're going to talk about a little bit more and quantify that in a bit. And so cells are normally their best condition to be in is when they are put in a hypotonic solution, so like a watery solution. So I have to water cells because that'll put pressure on the cell wall. In animal cells, though, if you put animal cells in a hypotonic solution, water's going to flow in, it's going to rupture the cell. So when a cell is placed in pure water, water is drawn into the cell because it's a hypotonic environment. And as I said, that drawing of water towards the cell has the potential, or the fact that the cell has the potential to draw water towards it, right? It's quantifiable, and it'll create a negative pressure, like a vacuum, like sucking in. Think of like sucking in a straw. You're drawing water towards you. The same thing happens in this case with the cell. So more solutes in the solution, the stronger the vacuum that there is. So the more salty or solute the solution, the more the vacuum is going to be, okay? And that's called, what we're going to quantify now, what's called solute potential. And it's measured in bars, and it's a measurement of pressure, okay? The opposite is also true. If a cell is placed in a salty environment, then the environment will have more ability to draw water towards it than the cell does, and then the water will get sucked out of the cell towards the environment, and that would be a hypertonic environment. So the more solutes you add to water, the stronger the pull towards those solutes. and the grade of negative pressure. Remember that negative is important because I want you to remember that. So in animal cells, if we put that cell in pure water, it has more solutes in the cell than the water. Water flows in and they pop and they rupture, as we mentioned before, because water is just going to keep flowing in. It'll never really reach equilibrium. But plants, on the other hand, they have a cell wall that provides pressure back, and that pressure, and it's going to keep flowing in until that pressure on the inside and the outside actually reaches equilibrium. Okay, the cell wall is equal to the solute potential. At that point, the pressure in the cell wall is equal to the solute potential, and therefore it won't rupture because it kind of provides a cage around the outside, whereas the animal cell would rupture in that case. All right. So other important things to remember, pure water has a solute potential of 0. That means the highest solute potential you can have is actually 0. The more solutes you add, the more negative pressure there is for drawing water towards it, right? The more solutes you add to pure water, the more negative that solute potential becomes. The stronger the vacuum, think about it like that. So if we do not know the solute potential, we have to calculate it. And really, there's a bunch of different things here, but the most important thing you have to understand is the concentration. The ionization constant is also important, which I'll talk about in 1 second. But the concentration is the big thing that affects it, and that's usually measured in molarity. So sometimes it's called osmolarity. It means the same thing. It's just a measurement of concentration and the ability for that concentration to cause osmosis. So that's what the C stands for. The I is the ionization constant. If it is a sugar, it doesn't ionize, it just dissolves. So its ionization constant is 1. But think about something like sodium chloride. If you had 1 mole of sodium chloride to 1 liter of water, that would be a 1 molar solution. But technically, because it splits into 2 ions, a sodium ion and a chloride ion, 1 positive, 1 negative, it actually has double the amount of drawing power that, say, sugar would have. So in that case, the ionization constant would be 2 if it ionizes. There are some things that don't fully ionize. If you took AP Chem, you probably learned that about their ionization constants. But really, in this course, all you're going to focus on 1 for sugar, 2 for salt. Okay, and they'll probably tell you that on the AP exam if it's anything other than 1. There's the pressure constant, which is just the constant that is measured. It's 0.0831 liter bars per mole degrees Kelvin, and then temperature in Kelvin. You have to put temperature in Kelvin because how quick the molecules are moving affects this as well. Remember, you take the degrees Celsius plus 273 for that. So let's calculate this. What is the solute potential for a solution that has a concentration of 2 molar of solute that has an ionization constant of 1? It doesn't break apart in ions at 27 C. All right, so the solute potential calculation is negative I CRT. And when you plug into this, if we look at this, right? Whoops. Let's see here. I will do the work. 1 second here. Will it let me? Maybe. I'll do it here like this. So we plug in each thing. So we go negative I, which because it's doesn't break, so it's negative 1. Okay. Times the concentration, which is 2 molar, times 2 moles per liter. Times the gas constant, which is 0.0831 liter times bar per mole per times Kelvin. Okay, and then temperature 273 plus 27, which is 300 K. Now, if you actually look at that, all plugged in. Notice that negative in front because it's always going to be a negative value because it's a negative pressure. If you do that, all of the units will cancel out. So notice how moles is on top, but moles is on the bottom of the gas constant. Cancels it out. Notice how liters is on the bottom there, but also it's on the top, right, up here at the 0.0831. So those cancel out. And then Kelvin is on the bottom right here. Or excuse me, Kelvin's on the top here, but it's on the bottom here. That cancels out. And what you're left with is bars, which is a measurement of pressure. Think about like barometric pressure. So when you do this calculation, you end up getting, let me do it real quick here. -1 times 2 times, -1 times 2 times 0.0831 times 300, you get equals -49.86 bars. And that's the answer. That means that's how strong that drawing power is for that solution. Okay. So that's solute potential, and then how you calculate it. Water potential, though, on the other hand, is designated by the solute potential plus the pressure potential. Now, solute potential must always be negative, but pressure potential can be positive or negative, but most cases pressure is going to be positive because it's going to kind of balance out the solute potential, especially in the case of plant cells. So the only time pressure potential is actually going to be important is in plant cells. Otherwise, it is going to be 0. So animal cells, pressure potential is 0. Plant cells, pressure potential it's probably going to be positive. And I'll show you how that kind of works later. So overall water potential is simply designated as solute potential plus pressure potential. Okay. And remember, it's just the ability for a solution to draw water across the membrane. Pure water has a solute potential of 0. And as I mentioned, in the case of animal cells, there's no pressure potential, only solute potential. Water will continually be drawn towards the solution with more solute inside the cell until the cell membrane ruptures. And because of that, especially if you put a cell in pure water, that's never going to happen, so it has to rupture. Okay. Remember, water will always flow just like from a high water concentration to a low water concentration. Water will flow from a high water potential to a low water potential, and this is where you can sometimes get confused because water potential is going to be, most of the time, it's going to be negative, right? Because pressure potential can make it different, but physiologically, water potential will be negative. So water should always flow from a high water potential to a low water potential, or a less negative number towards a more negative number. The bigger the number in the negative zone, the lower it is, right? So -20 is lower than -5. So water will flow towards the solution that has a water potential of -5 towards where there's -20. So don't get that confused, okay? As I mentioned, in a plant cell, once the pressure potential and the solute potential are equal, there's no net flow of water into or out of the cell anymore, and the cell will not lyse or split. But there's pressure pushing on the cell wall, and we'll call that turgor pressure. Okay, so turgor pressure is what causes the plants to stand up. And you can see here, so distilled water has a solute and pressure potential. So the atmospheric pressure is going to be equal for everything, so we're not going to worry about pressure potential in just an open container. So solute potential and pressure potential is 0. When you initially put the plant into the distilled water, it has a solute potential of -2 because there's solutes inside the plant cell. So water is going to flow in. It's going to continually flow in until it reaches equilibrium. It's not going to burst, but it's going to keep flowing in until the pressure is pushing, the cell wall is pushing against the plant cell, and the plant cell is pushing against the cell wall in an equal but opposite direction as the solute potential. And it's going to hit equilibrium. So the overall water potential is now 0 because that solution isn't drawing water towards it anymore because there's that pressure on the outside. Right? It wants to explode, but the cell wall won't let it, and it's putting 2 bars of pressure on that cell wall. So this is a non-living example using what's called a U-tube, not to be confused with YouTube, the whatever video service. So that's a U-tube. It's shaped like a U. And what you see here is when we have pure water naturally, and we put solutes on the other side, and we put a semi-permeable membrane in between, right at the bottom of the U, water is going to flow from a high water concentration to the low water concentration, or from the left side towards the right. And notice how the water level on the one side will actually rise a little bit, okay, until atmospheric pressure kind of takes over and gravity takes over. Now what you could do is you could then put on this side, we could add a positive pressure potential. So notice it's then pushing on this side, right, with 2.23 millipascals, which is, I think, like 1,000 bars of pressure. It's a different unit of pressure, pushing on it, and we can reach equilibrium again. So we can push with that pressure on the other side. Or what we can do is we can actually continue pushing hard on this side, right, increasing it, and what's going to happen is it's going to push water through the other side. It's going to overcome that solute potential. So there's actually 0.07 millipascals of pushing on this side. It's not negative because it's not on this side. It's actually pushing from the solute side. That's why that's then positive, but that doesn't really happen in nature. You can also put a negative pressure on the other side, so instead of having solutes on that side, we're going to actually draw it up with this piston, and then we can still suck water through it. And that's actually how reverse osmosis works. If you have a water filtration that's a reverse osmosis, they force the water using negative pressure through a semi-permeable membrane, preventing solutes from crossing and purifying the water. So to figure out which way water will flow, you need to calculate the water potential of the inside of the cell and the water potential in the solution in the cell. Remember, in most cases, pressure potential will be 0. So you calculate water or solute potential on the inside of the cell and on the outside of the cell in the environment. Water will flow from the higher water potential to the lower water potential, or from the less negative to the more negative number. And remember, that means something similar to, but not the same thing, as water will flow from a high water concentration to a low water concentration. So that's water potential. We're going to practice this more in class. I have some problems which I will help you out with when we get there. If you have any questions, please come see me.